Hello, everyone, and welcome. I'm glad you're here today. We're about to dive into an exciting topic, nutrient cycling. Today's presentation will explore how essential nutrients move through our environment, supporting life on Earth. We'll cover the basics of nutrient cycles, their importance, and how they impact ecosystems. So let's get started and explore this fascinating subject together. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Today, I want to talk about the nitrogen cycle, which is a fundamental process in ecology and environmental science. The nitrogen cycle describes how nitrogen moves through the environment, living organisms, and the atmosphere. It's a key part of understanding how ecosystems function and sustain life. First, nitrogen is essential for all living things because it's a major component of amino acids and DNA. However, most organisms can't use atmospheric nitrogen directly, so it has to be converted into forms they can use. That's where the cycle gets interesting. The process begins with nitrogen fixation, where certain bacteria convert atmospheric nitrogen into ammonia. This ammonia can then be transformed into nitrites and nitrates through nitrification, making it accessible for plants. Plants absorb these nitrates and incorporate them into their tissues. When animals eat plants, they take in nitrogen, and through their waste and eventually decomposition, nitrogen is returned to the soil as ammonium. This is part of the aminification process. Then, through nitrification, nitrates are produced again, continuing the cycle. Finally, some bacteria perform denitrification, converting nitrates back into atmospheric nitrogen, completing the cycle. This process helps maintain a balance in nitrogen levels and prevents excess accumulation in the soil. Understanding the nitrogen cycle highlights how interconnected life and environmental processes are, and it emphasizes the importance of microbial activity in maintaining ecosystem health. It also ties into our broader discussion of how biogeochemical cycles sustain life on Earth. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the end cycle. The end cycle is a fundamental process in ecosystems because it governs how nitrogen moves and transforms in the environment. Nitrogen is essential for all living organisms since it's a key component of amino acids and nucleic acids. The cycle begins with nitrogen fixation, where certain bacteria convert atmospheric nitrogen gas into forms that plants can absorb, like ammonium. Then, through processes like nitrification, ammonium is transformed into nitrate, which plants readily take up. Plants use this nitrogen to grow, and when they die or excrete waste, nitrogen returns to the soil as organic matter. Decomposition then releases ammonium again in a process called aminification. Nitrification continues with bacteria converting ammonium back into nitrate, maintaining a balance. And finally, denitrification occurs when bacteria convert nitrate back into atmospheric nitrogen, completing the cycle. Understanding this cycle highlights the interconnectedness of biological and chemical processes, and it's crucial for managing ecosystems and agricultural practices sustainably. It also ties into the overall theme of nutrient cycling and ecosystem health that we've been exploring throughout this presentation. Let's take a closer look at the nitrogen cycle in soil. This cycle is essential because nitrogen is a vital nutrient for plant growth, but it doesn't just stay in one form. It undergoes several transformations. First, nitrogen in the atmosphere is converted into ammonium through a process called nitrogen fixation, which is often carried out by bacteria in the soil. Then, ammonium can be transformed into nitrites and nitrates through nitrification, making it accessible for plants to absorb. When plants take up these nitrates, they incorporate nitrogen into their tissues. After plants and animals die or excrete waste, the nitrogen returns to the soil as organic matter. This organic nitrogen is then mineralized back into ammonium, completing the cycle. Understanding this process highlights how soil health and microbial activity are crucial for maintaining a sustainable nitrogen supply, which directly supports healthy plant growth and overall ecosystem productivity. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the phosphorus cycle. Phosphorus is a vital element for life, essential for DNA, RNA, and energy transfer within cells. Unlike other biogeochemical cycles, the phosphorus cycle doesn't involve a gaseous phase. Instead, it mainly moves through the soil, water, and living organisms. Phosphorus starts in rocks as phosphate minerals. Through weathering processes, these minerals gradually break down, releasing phosphate ions into the soil and water. Plants then absorb these phosphates, which are passed up the food chain as animals eat plants and other animals. When organisms die or excrete waste, the phosphorus returns to the soil or water, where it can be reused or deposited into sediments. An important aspect to highlight here is how human activities, like mining and the use of fertilizers, can significantly impact this cycle by increasing phosphate levels in certain areas, which can lead to environmental issues like eutrophication in water bodies. Understanding the phosphorus cycle is crucial because it underscores the interconnectedness of geological processes, ecosystems, and human influence, tying back to our overall theme of how biogeochemical cycles sustain life on Earth. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. The carbon cycle actually fits the generalized scheme of biogeochemical cycles a bit better than the water cycle does. What I mean by that is, the way carbon moves through the environment involves a lot of different reservoirs, like the atmosphere, oceans, soil, and living organisms, and it exchanges between these reservoirs in complex ways. This pattern of movement, where carbon is taken up, stored, released, and transferred, is really characteristic of biogeochemical cycles overall. So, understanding the carbon cycle helps us see broader themes about how different elements cycle through the Earth system, highlighting the interconnectedness of biological, chemical, and physical processes. Let's take a look at the global sulfur cycle. Sulfur is a vital element in Earth systems, and it moves through various reservoirs in the environment. This cycle involves both natural processes and human activities. For example, volcanic eruptions release sulfur gases into the atmosphere, while weathering of rocks gradually releases sulfur compounds. In the atmosphere, sulfur can form sulfate aerosols, which influence climate by reflecting sunlight. These aerosols can eventually fall back to the Earth's surface through precipitation, completing part of the cycle. Human activities, such as burning fossil fuels, have significantly increased atmospheric sulfur levels, leading to issues like acid rain. Understanding this cycle helps us grasp how interconnected Earth's processes are and highlights the importance of managing anthropogenic impacts to protect environmental health. This slide doesn't contain enough information. That's why we're moving to the next slide. The water cycle is really more of a physical process than a chemical one. What that means is that it mainly involves changes in the state of water, like evaporation, condensation, and precipitation, rather than chemical reactions. These steps are all about physical changes, such as water turning from liquid to vapor and back again. It's a continuous, natural cycle that moves water around our planet, shaping weather patterns and supporting life. Understanding this helps us see how vital physical processes are to the Earth's systems, especially when we consider how they connect to the larger themes of environmental balance and sustainability. Let's take a closer look at the water cycle. The water cycle, also known as the hydrological cycle, is a continuous process that moves water around our planet. It all begins with evaporation, where the sun heats up water in lakes, rivers, and oceans, turning it into vapor. This vapor rises into the atmosphere. Once in the air, the water vapor cools and condenses to form clouds, which is called condensation. When the clouds become heavy enough, the water falls back to the earth as precipitation, rain, snow, sleet, or hail. This process replenishes water in the ground and on the surface. Some of this water infiltrates the soil, feeding plants or becoming groundwater, while some runs off into water bodies, continuing the cycle. This cycle is fundamental to sustaining life, regulating climate, and shaping our environment. Understanding the water cycle helps us appreciate how interconnected natural systems are, and it highlights the importance of conserving water resources for the future. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at biogeochemistry. This field is all about understanding the interactions between biological processes and the Earth's geochemical cycles. It's fascinating because it shows how living organisms influence and are influenced by the chemical composition of their environment. For example, microbes play a crucial role in cycling nutrients like nitrogen and carbon, which are essential for life. These processes help regulate the Earth's climate and support ecosystems. Connecting this to our overall theme, biogeochemistry helps us see how life and Earth's chemistry are interconnected, highlighting the importance of sustainable interactions between biological systems and the environment. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about biogeochemistry, which is essentially the study of the chemical processes that happen in the atmosphere, oceans, and land ecosystems. It also looks at how elements are transferred between these different parts of our environment. This science helps us understand the complex interactions that sustain life on Earth. There are two main types of processes in biogeochemistry. The first involves physical events, such as the release of volatile elements into the atmosphere. Think of it as natural events like volcanic eruptions or evaporation that release chemicals into the air. The second type of process is directly related to biological activity. For example, nitrogen loss from forests or wetlands to the atmosphere happens because of biological processes like respiration or decomposition. These processes are crucial because they control how nutrients cycle through ecosystems and how they impact our climate. By understanding these processes, we're better equipped to see how Earth's systems are interconnected and how human activities might influence these natural cycles. This ties back into the overall theme of understanding the Earth's complex and dynamic environment. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about forest biogeochemistry, focusing on nutrient cycles. These cycles are crucial because they describe how nutrients move and transform within and between ecosystems. When we refer to intersystem cycles, we're talking about the movement of nutrients between a forest ecosystem and other ecosystems on Earth's surface. This could involve processes like nutrient runoff into streams or deposition from the atmosphere. On the other hand, intrasystem cycles describe how nutrients move within a single forest. This includes processes like the uptake of nutrients by plants, their incorporation into biomass, and their return to the soil through decomposition. Understanding these cycles helps us see how forests sustain themselves and interact with the broader environment, which is central to our overall theme of ecosystem health and sustainability. Let's take a closer look at the ecosystem inputs. First, we have the atmosphere, which plays a crucial role in supplying key nutrients. Through processes like nitrogen fixation and rock weathering, nutrients are released into the environment. Hydrological inputs, such as rainfall and snowfall, are also vital because they bring nutrients like nitrogen directly to the ecosystem. Now, when we think about carbon sources, photosynthesis stands out as the primary process that introduces carbon into the system, supporting plant growth and energy flow. Rainfall and snowfall don't just deliver water, they also carry important nutrients, including nitrogen, which are essential for plant and microbial life. In forest ecosystems, elements like nitrogen, sulfur, and chlorine are fundamental. They're involved in various biological and chemical processes that sustain the forest's health and productivity. Wetlands, on the other hand, have a unique role in releasing gases. They tend to emit reduced forms of nitrogen and sulfur gases, which are part of the natural greenhouse gas cycle. Lightning is another interesting input. It produces gaseous oxides of nitrogen, which can influence atmospheric chemistry and nutrient cycles. Volcanic eruptions also contribute by releasing gases like sulfur dioxide or SO2, which can impact air quality and climate. So, in summary, these natural processes and sources, from atmospheric gases, weathering, biological activity, to geological events, are all interconnected inputs that drive and sustain the complex functioning of ecosystems. When a volcano erupts, it releases sulfur dioxide, or SO2, into the atmosphere. These gases don't just stay in the air. They can react with rainwater and groundwater, leading to some important chemical processes. For example, SO2 reacts with oxygen to form sulfur trioxide, or SO3. This SO3 can then combine with water, creating sulfuric acid, H2SO4. When sulfuric acid dissolves in water, it releases hydrogen ions, H+, and sulfate ions, SO42, which are key contributors to acid rain. It's also important to note that the main industries around us emit nitrogen dioxide, NO2, and sulfur dioxide, SO2, into the atmosphere. These pollutants play a significant role in acid rain formation and air quality issues. Overall, understanding these chemical reactions helps us grasp how volcanic activity and industrial emissions impact our environment. Let's take a closer look at how nutrients enter ecosystems. One key process is biological fixation of atmospheric nitrogen, where certain organisms like bacteria convert nitrogen, gas from the air, into forms that plants can use. This is crucial because nitrogen is often a limiting nutrient in many ecosystems. Another important pathway is weathering, which involves the breakdown of rocks and minerals over time. Through this natural process, nutrients like potassium, calcium, and magnesium are released into the soil, enriching the ecosystem. Deposition also plays a significant role. This includes nutrients falling from the atmosphere via rain, dust, or gases. These inputs can vary depending on environmental conditions and human activities, but they are vital sources of nutrients that support plant growth. Together, these processes highlight the diverse ways nutrients are supplied to ecosystems, maintaining their productivity and balance. Understanding these inputs helps us see how ecosystems are sustained and how they might respond to changes in environmental conditions. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about nitrogen fixation, which is the process of converting atmospheric nitrogen, N2, into a form that organisms can use, like ammonium, NH4+. This process requires a lot of energy and also depends on the presence of phosphorus, or P. It's important to note that oxygen actually inhibits this process because it can damage the nitrogenase enzyme responsible for fixing nitrogen. Carried out mainly by bacteria, nitrogen fixation can happen in different ways. One key method is symbiotic nitrogen fixation, which occurs in partnership with plants like legumes and alder trees. These plants host bacteria in their root nodules that perform the fixation for them. Another way is heterotrophic nitrogen fixation, which takes place in the rhizosphere, the zone around plant roots, or other carbon-rich environments where bacteria can thrive. We also see phototrophs, like blue-green algae, playing a role here. These organisms use light energy to help power the fixation process. Overall, nitrogen fixation is crucial because it provides the bioavailable nitrogen that supports plant growth and sustains entire ecosystems. Understanding these different mechanisms helps us see how nitrogen cycles through our environment, linking energy, microbial activity, and plant life in a really interconnected way. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about rock weathering as a source of nitrogen. Some sedimentary rocks actually contain quite a bit of nitrogen, and when these rocks weather, they can release nitrogen into the environment at pretty high rates, up to 2 grams of nitrogen per square meter per year. That's a significant contribution. However, it's important to note that most rocks don't contain much nitrogen at all. So, while certain rocks can be important sources, in general, the nitrogen contribution from rock weathering varies greatly depending on the type of rock. This process plays a role in the broader nitrogen cycle, connecting geological processes with nutrient availability in ecosystems. Let's talk about the sea and its crucial role in our planet's systems. When we look at the sea surface, we see bubbles forming and bursting. These bubbles are responsible for releasing about 10 billion tons of salt into the atmosphere each year. This process is a key part of how salts like sodium, magnesium, chloride, and sulfate get cycled through the environment. These tiny water droplets, known as aerosols, are formed in the atmosphere from these sea surface bubbles. They act as nuclei for cloud formation and influence weather patterns. When the water evaporates from these aerosols, it leaves behind salts and other particles, which then become part of the atmospheric composition. So, in essence, the sea is not just a vast body of water, but a dynamic system that continuously interacts with the atmosphere, contributing to climate regulation and the distribution of key minerals across the globe. This connection between the ocean and atmosphere highlights the importance of understanding these natural processes in our overall climate system. Let's talk about biotic accumulation and storage, which is a key part of nutrient cycling during forest development. As forests grow, they accumulate nutrients in various ways, and this process is essential for maintaining healthy ecosystems. Tree growth plays a significant role here because it influences the cycling of nutrients between different parts of the system. When trees grow, they store nutrients in different tissues, and these tissues can be categorized based on their lifespan. For example, short-lived tissues like leaves are produced and shed annually, so they quickly cycle nutrients back into the environment. On the other hand, long-lived tissues such as wood can store nutrients for many years, acting as a more stable reservoir. Understanding how these tissues contribute to nutrient accumulation helps us see the bigger picture of how forests develop and sustain themselves over time. It also highlights the importance of different tissue types in maintaining nutrient balance within the ecosystem. As the tree development progresses, we see a corresponding increase in soil volume and a rise in nutrient accumulation. This means that as trees grow, they contribute to building up the soil and storing more nutrients, supporting further growth. In the early stages of succession, trees and shrubs tend to rapidly accumulate nutrients, quickly establishing the foundation for more complex ecosystems. However, in old-growth forests, nutrient storage tends to reach a plateau, either stabilizing at a certain level or cycling over time. This indicates a balance where nutrient input and output are more or less in equilibrium. Interestingly, the amount of nutrients stored in the forest floor is quite similar to that stored in the organic matter of the soil during different stages of plant succession. This highlights the close relationship between plant development and soil nutrient dynamics, reinforcing the idea that as forests mature, nutrient storage patterns evolve but tend to stabilize, ensuring the sustainability of these ecosystems over the long term. During secondary succession, the changes in organic matter or nutrient pool minerals are actually quite minimal. However, over time, there's a general decrease in nutrient levels. This happens because nutrients are added unevenly, meaning some are lost faster than they are replenished. The main driver of this nutrient loss is increased decomposition, which speeds up the breakdown of organic material and releases nutrients into the environment. Because of these processes, it typically takes about 60 to 80 years for the forest floor to fully recover. This long recovery time highlights how gradual and complex nutrient cycling is during succession, and it emphasizes the importance of understanding these dynamics when studying ecosystem recovery and health. Let's take a look at nutrient storage in forest ecosystems. As we move from boreal to tropical forests, the storage of nutrients generally increases. This means tropical forests tend to hold more nutrients overall compared to boreal forests. Now, when we consider the nutrient content of the forest floor, it actually increases from boreal to tropical forests, which is the opposite trend of total nutrient storage. Interestingly, organic matter, or OM, in the forest floor is higher in boreal forests compared to tropical ones. Leaves, on the other hand, contain about 5 to 20% of the total nutrients, but they only make up a small fraction of the organic matter in the ecosystem. Above-ground biomass includes a significant portion of organic matter, roughly 20 to 50%. When we look at nitrogen, the above-ground parts contain about 4 to 8% of the total nitrogen within the forest ecosystem. In tropical forests, a larger percentage of nitrogen is stored in these above-ground components compared to temperate forests. Finally, short-lived tissues like leaves and fine roots play a crucial role in nutrient cycling, as their rapid turnover determines the annual movement and availability of nutrients within the ecosystem. Understanding these dynamics helps us appreciate how different forest types manage and store nutrients differently, which is key to grasping the overall functioning of forest ecosystems. Now, let's take a closer look at ecosystem losses, focusing on streams and groundwaters. These water bodies play a crucial role in transporting nutrients and minerals within an ecosystem. When water flows through streams, it interacts with the surrounding soil and bedrock, leading to weathering processes. This weathering releases minerals into the water, which are then carried along the stream. The water in streams contains dissolved ions, which are essential for various biological processes, and it also transports particles. These particles can be organic, like decomposed plant material, or inorganic, such as mineral fragments. This process of carrying particles is a key aspect of mechanical weathering, helping break down rocks and soil over time. It's also important to note that in undisturbed forests, the organic matter lost from the soil is about 15% of the net primary production. This loss reflects natural decomposition processes and nutrient cycling within healthy ecosystems. Overall, these processes highlight how water not only sustains life, but also drives the chemical and physical changes in ecosystems, linking water chemistry, weathering, and biological activity in a dynamic system. In undisturbed forests, most of the plant nutrient loss happens in dissolved form, which means these nutrients are carried away in the water that flows through the soil and into nearby water bodies. When we look at the concentration of these dissolved substances, they are closely related to the volume of water discharge. So the more water moves through, the more nutrients are lost. It's important to note that in these undisturbed forests, the chemical composition of what's dissolved remains relatively constant over time, indicating a stable soil and plant system. When we examine the overall cation losses, calcium tends to be lost the most, followed by sodium, magnesium, and potassium. This order reflects how different nutrients are mobilized and transported in the ecosystem. Additionally, bicarbonate ions are the dominant form involved in weathering reactions in these forests. This suggests that bicarbonate plays a key role in the natural breakdown of minerals, which releases essential nutrients into the soil and influences the chemistry of the environment. All these points highlight how, in a natural, undisturbed forest system, nutrient cycling is quite balanced, with the dominant weathering processes and consistent chemical composition helping maintain the health of the ecosystem. On this slide, we're looking at the gaseous and particulate losses to the atmosphere that occur in wetland environments. One of the key gases involved is methane, which is produced under anaerobic conditions, meaning without oxygen, in wetland soils. Similarly, hydrogen sulfide, or H2S, is also generated in these environments. When we have a thick organic matter layer combined with rain, it creates an anaerobic setting where these gases can form and eventually escape into the atmosphere. The low oxygen difference between these wetland layers and the soil layers facilitates processes like denitrification, where nitrogen compounds are transformed into N2 or N2O gases that are released into the air. Additionally, sulfur compounds are released from bogs, swamps, floodplains, and forested wetlands. These areas emit sulfur gases, including hydrogen sulfide and other sulfur gases, which can be directly released as sulfide or other particulate forms. Understanding these processes is crucial because they highlight how wetlands contribute to atmospheric greenhouse gases and other emissions, linking back to the overall theme of biogeochemical cycles and environmental impact. Plants can actually play a role in directing the sources of gaseous and particulate nutrient loss. For example, in forests, we see volatile emissions like terpenes, which are organic compounds that can carry nutrients away from the plant system. These volatile compounds often contain nitrogen and sulfur, which are essential nutrients but can be lost through these emissions. Additionally, plants release gases like hydrogen sulfide, H2S, and ammonia, NH3, directly from their leaves. These processes can significantly influence nutrient cycling in ecosystems, highlighting how plants are not just passive players, but active participants in nutrient dynamics. Understanding these emissions helps us grasp the complex ways nutrients are cycled and lost in natural environments. Now, let's talk about nutrient losses in fire. When a fire occurs, nutrients are lost through gases and particles that become part of the smoke. These losses can have significant impacts on soil health and recovery. For example, increased runoff and erosion happen because the fire exposes the soil, making it more vulnerable to water and wind damage. If you burn leaves, about 85% of the nitrogen content is lost, which is quite substantial. In forest fires, the amount of volatile nitrogen released correlates with the heat generated and how much organic matter is consumed. It's interesting to note that nitrogen losses are typically the highest, followed by potassium, magnesium, calcium, and phosphorus. Other nutrients tend to be less affected or not lost at all. Understanding these nutrient losses helps us grasp the broader impact of fire on ecosystems and soil fertility, emphasizing the importance of managing fires carefully to preserve vital nutrients. On this slide, I want to highlight how nutrient inputs, specifically nitrogen, are quite low due to weathering processes. It takes a significant amount of time for these nutrients to reach their original levels after being depleted. For example, in a pine forest, the nitrogen that is released due to fire can range from 11 to 40 kilograms per hectare. To put that into perspective, this amount is equivalent to 3 to 12 times the annual nitrogen input that the ecosystem normally receives. This shows us that fire can cause a substantial loss of nutrients, but we can keep these losses low by managing the fuel load effectively. Reducing fuel load minimizes the risk of intense fires, which in turn helps preserve soil nutrients. When a fire does happen, it burns above ground biomass and releases ash, which contains some nutrients. However, frequent or severe fires can deplete these nutrients over time, impacting the overall health of the ecosystem. So, the key takeaway here is that controlling fire and fuel loads is crucial for maintaining nutrient balance and supporting the resilience of ecosystems like pine forests. This connects directly to the overall theme of sustainable management and understanding natural processes that influence forest health. When we consider the concept of rain after fire, one of the key points to remember is that it can lead to a high and readily available supply of nutrients. However, this also means that there's a greater potential for nutrient runoff. This runoff can result in significant nutrient loss from the soil, which can impact the overall health of the ecosystem. But it's important to note that these losses are not fixed. They depend on several factors. For instance, the season plays a big role. Whether it's during the rainy season or drier months can influence how much nutrient is lost. Rainfall intensity and duration are also crucial. More intense or prolonged rains tend to cause more runoff. Another factor is the growth of positive vegetation. If plants are actively growing and cover the soil well, they can help absorb nutrients and reduce runoff. So, understanding these variables helps us better manage post-fire landscapes and mitigate nutrient loss, which ties back to the overall goal of maintaining healthy ecosystems after disturbances like fire. Now, let's take a closer look at nutrient losses in forest harvests. When we talk about natural harvests, the process is quite different from commercial clear cuts. In natural harvesting, the amount of wood biomass removed is relatively small, accounting for just a tiny percentage of the total elements in the forest ecosystem. This means that most nutrients stay within the forest, maintaining its health and productivity. In contrast, with commercial clear cuts, there's a more significant removal of biomass, which can lead to some nutrient loss. However, it's important to note that even then, the actual loss of nutrients is still a small percentage of the overall nutrient pool. Another key point is what gets left behind. Foliage and branches are usually left on site after a harvest, and these contain a large portion of the nutrients. So, while some nutrients are temporarily lost when biomass is removed, the nutrients remaining in the foliage and branches help sustain the forest's nutrient cycle. Overall, understanding these nutrient losses helps us better appreciate how different harvesting methods impact forest health and how we can manage these impacts sustainably. When we harvest the whole tree for pulpwood or biomass energy, there's often more nutrient loss compared to partial harvesting. This is because removing the entire tree takes away not just the wood, but also the nutrients stored in the foliage and roots. After clear cutting, the soil's environment changes significantly. Specifically, the population of nitrifying bacteria in the soil tends to increase. These bacteria play a crucial role in converting organic nitrogen into nitrate, or NO3. During this process, a large amount of NO3 can be produced from the decaying litter left behind. Now, organic nitrogen, which is bound in plant material, gets transformed into ammonium, NH4+, and then into nitrate, NO3. This nitrate is highly soluble and mobile in the soil. If there's no regrowth of vegetation, no new plants to uptake these nutrients, the NO3 will simply be leached away by water moving through the soil profile. This nutrient leaching is a concern because it leads to nutrient loss from the soil, which can impair future plant growth and affect the overall health of the ecosystem. So, understanding this process helps us see why careful management after harvesting is so important to maintain soil fertility and sustainability. Let's talk about biogeochemical cycles. These cycles describe how simple inorganic substances from the atmosphere are transformed into complex organic materials. This process is essential for supporting life on Earth. There are two main factors at play here. First, energy flow, which moves in one direction. Think of it as a one-way street where energy is constantly entering, moving through, and then leaving the system. Second, matter movement, which follows a circular path. Unlike energy, matter cycles continuously within the environment, moving through different forms and reservoirs. These cycles are fundamental to understanding how nutrients and elements are recycled in ecosystems, helping to maintain the balance that sustains life. Connecting this to the bigger picture, these cycles illustrate how interconnected and dynamic our planet's systems really are. Let's talk about nutrients, which are essential for plant growth and development. First, we have the macronutrients. These are the elements that plants need in relatively large amounts, such as calcium, hydrogen, oxygen, nitrogen, phosphorus, potassium, magnesium, and sulfur. Each of these plays a vital role. For example, nitrogen is crucial for leaf growth, while phosphorus supports root development and flowering. Moving on to micronutrients. These are required in smaller quantities, but are just as important. Micronutrients include iron, manganese, copper, zinc, boron, sodium, molybdenum, and chloride. Additionally, some other elements like vanadium and cobalt are also considered micronutrients in certain contexts. Even though these are needed in trace amounts, deficiencies can significantly affect plant health and productivity. Understanding the distinction between macro and micronutrients helps us better manage soil and plant health, ensuring that plants get the right balance for optimal growth. This balance is fundamental to the overall theme of sustainable and effective crop production. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's wrap up with nutrient cycling. First, we have cycling by microorganisms. Microorganisms play a crucial role in breaking down and transforming nutrients in the environment. Air acts as a reservoir for key elements like sulfur and nitrogen, facilitating their movement through different parts of the cycle. For example, sulfur and nitrogen cycles are driven by microbial activity, making these processes vital for maintaining ecosystem health. Next, we look at sedimentary cycles. These are influenced significantly by human activities, such as mining, agriculture, and pollution, which can disrupt natural processes. Sedimentary cycles involve the movement of nutrients through soils and sediments, often over long periods. Overall, understanding these cycles helps us see how interconnected life and the environment are, especially as human impacts continue to shape these natural processes. Recognizing the importance of microbial activity and human influence is key to managing and protecting our ecosystems effectively.